Okay, welcome you all for this new session on multi-degree of freedom system. Okay, in this module where they explain different numerical methods to solve the vibration problems. In the vibration problems, the main thing is to find the natural frequency of the system. Stodola method, it is one of the numerical method to find the natural frequency of the system. By the Stodola method, we are solving the vibration problem, that is for the multi-degree freedom of system. What is multi-degree of freedom system? If the number of coordinates required to define the positions, if it is more than 3, then it is called as the multi-degree of freedom system. We already know how to find the natural frequency of the system for the single degree of freedom systems by Newton's method and energy method. But for the multi-degree freedom of system, it is not so easy. So we are using the numerical methods. Stodola method, it is one of the numerical method. Okay, let us start the Stodola method. We are using Stodola method to find the natural frequency of the systems for the multi-degree of freedom system. Okay, let's start the Stodola method. In the Stodola method, it is a iterative method. Okay, let us start with a problem. It is a 3 degree of freedom system where there are 3 springs and 3 masses. Okay, for each mass and for each springs we are created a column here, and to write particulars one column. So for 3 springs and 3 masses, total 6 elements are there. Spring 1, mass 1, spring 2, mass 2, spring 3, mass 3, total 6 elements. 6 plus 1, we need to create 7 columns here. Okay, then you take all the values here. First column for the particulars and first spring, that is K1, then mass 1, then stiffness 2, spring 2, mass 2, spring 3 and mass 3. So total 6 elements, so 6 plus 1 columns. Next, in this method, in the Stodola method, you have to take all these particulars, that is assumed deflection, inertia force, spring deflection and calculated deflection. Okay, for in this problem, masses, all the masses have 2 kg and spring stiffness is 20 Newton per meter. Okay, first in the first row, it is assumed deflection. You have to assume the masses, that is 1 1 1. You may assume with different values also. Okay, now first one, the assumed deflection of the masses 1 is 1, mass 2 is 1 and mass 3 is 1. It is assumed value. You can also assume some other value also. Next, in the inertia force, you are assuming the deflections in the masses column only. Okay, I assumed the deflection value for the mass 1 is 1, mass 2 is 1 and mass 3 is 1. And then next step, you are finding the inertia force. How to find the inertia force? That is, this is the formula to find the inertia force for the masses. M omega square into x. M is the mass and x is the deflection. M, to find the inertia force for this mass, how much is the mass? It is 2 kg. 2 into omega square into this x is the deflection of the corresponding mass. Deflection is, it is assumed value 1, so it is 2 omega square. Similarly, you find inertia force for the mass 2 and mass 3. Then you need to find spring force. How to find this spring force? For you have to write spring force in the spring column only, in the stiffness columns only, not in the mass column, masses columns. How to find the spring force? All the sum of inertia force, 2 omega square plus 2 omega square plus 2 omega square, all the sum of the inertia force on the right side, that is plus 2 omega square plus 2 plus 2, 6 omega square. Similarly, inertia force on the right side, 2 plus 2, it is 4 omega square. Similarly, only one spring force on the right side, that is 2 omega square. Next, spring deflection. Spring deflection means spring force divided by stiffness values. Spring force divided by stiffness value, 6 omega square divided by 20, it is 0.3. Similarly, spring force divided by stiffness, that is 0.2 omega square. Similarly, spring force divided by this stiffness value, 0.1 omega square. Now you find the calculated deflection. Okay, it is all the spring deflection on the left side only this deflection is there, 0.3 omega square. Similarly, all the deflections on the left side, 0.3 omega square and 0.2, so it is 0.5 omega square. Similarly, you find deflection value on the left side, 0.3 plus 0.2 plus 0.1, it is 0.6 omega square. Now we have deflection values 0.3 omega square, 0.5 omega square, 0.6 omega square for mass 1, mass 2 and mass 3. You normalize it to as 1, normalize it as 1 means if 0.3 omega square is 1, you assume it 0.3 omega square is equal to 1. If 0.3 omega square is equal to 1, then what is 0.5 omega square? Okay, or 0.5 omega square divided by 0.3 omega square, that is 1.67. Similarly, 0.6 omega square divided by 0.3 omega square, that is 2. Okay, now in this first trial, okay, by the first trial the deflection values are 1, 1.67, 2. The assumed deflections are 1, 1, 1, but by the calculation the new deflection values are 1, 1.67, 2. Okay, we are repeating the same procedure now by taking the new values, that is 1, 1.67, 2. Okay, this is trial 2, 1, 1.67, 2. Okay, again you are repeating the same steps, but in the previous steps the values are 1, 1, 1, the assumed deflections. Now by taking these values 1, 1.67, 2. Okay, you just repeat the trial 2. So the new deflections are 1, 1.79 and 2.2. For these values again we are repeating. You have to repeat until you will get the two values, two results which are closer to each other. See here, the deflection 1, 1, it is always 1, 1. 1.79, 1.8, it is close. 2.21, 2.24, it is close. Now you can stop for these values, or maximum you do 3 iterations. Okay, so the deflections are 1 for the mass 1, 1.8 for the mass 2 and 2.24 for the mass 3. Then to find the natural frequency, you add all the deflections, 0.5 plus 0.9 plus 1.1. This is equal to 1 plus 1.8, 2.2, or sum of calculated deflection rho, that is equal to sum of these values. By this you find what is the omega value. This omega value, it is the natural frequency for this system. Okay, this is the Stodola method. By the Stodola method you are finding the natural frequency of the system for the multi degree of freedom system. Okay, thank you.